After studying this module, you shall be able to know about the entropy balance equation, learn how the entropy production is related to affinity of the reaction, learn how the fluxes and forces are transformed, and about non-equilibrium stationary states briefly. Find out the relationship between the rate of entropy production and coefficient of thermal conductivity. Discuss various laws regarding different transport processes. Entropy balance equation. The basic equation for non-equilibrium thermodynamics is entropy balance equation. This balance equation for entropy can be derived using the concept of conservation of energy and the balance equation for the concentration. This equation depicts the relationship between three thermodynamic quantities. They are the entropy change, the entropy production, and the entropy flow. The change in entropy is the time derivative of the entropy of the system, and it is the sum of two integrals, entropy production and entropy flow for a given system. And the expression is given by ds internal by dt denotes the entropy production and is written by the integral of sigma into dV. This time derivative of entropy denotes the entropy produced within the system. The time derivative of external entropy denotes the entropy flow, and the expression is given by integral of negative divergence of J into dV. It is the time derivative of that entropy which comes from or goes out to the environment across the boundary of the system. Thus, the final expression for change in entropy is given by the integral sigma minus divergence of J into dV. For a reaction diffusion system, the entropy production comprises of two components, the entropy production of chemical reactions and diffusions, respectively. The total entropy production can be written as the sum of sigma r dV and sigma dV. From the expression, you can see that Kb denotes the Boltzmann constant, R rho plus and R rho minus represents the rate of forward and backward reactions of the rhoth chemical reaction. Dj and Cj represents the diffusion coefficient and the concentration of the jth component respectively. Transformation of generalized fluxes and forces. The rate of entropy production for an irreversible process is given by the summation of Ji into Xi, which is greater than 0. For a single chemical reaction occurring at a given rate, the expression can be written as the product of J and X. Sigma does not depend on the reaction sequence but depends on the linear combination of forces and flows. In the equation, the flux J is identified with the rate R and generalized forces X is identified with the affinity. Consider a consecutive type of reaction in which A gives B and in the second reaction B gives C. For the reaction 1, the affinity is given by the difference of mu A minus mu B, since Ra is equals to Rb is equals to 1. Similarly, for reaction 2, the affinity is given by mu B minus mu C, since Rb is equals to Rc, which is equals to 1. The change in number of moles of A per unit time or rate of reaction is given by dNA by dt is equals to minus R1. Similarly, the change in number of moles of C per unit time is given by dNc by dt is equals to R2. Hence, the change in number of moles of B per unit time is given by R1 minus R2. We know that the rate of entropy production for reaction 1 and 2 is equals to A into R1 plus A into R2. Now, consider a different chemical reaction in which A gives C and B also gives C. The corresponding affinities of the reaction 1' and 2' are: for A1 prime it is equals to A1 plus A2, and for A2 prime it is equals to A2. Therefore, the change in number of moles of C is equals to R1 prime plus R2 prime. By comparing equation 6, 7, 8 with equation 12, we find that R1 is equals to R1 prime and R2 is equals to R1 prime plus R2 prime. For this reaction, the rate of entropy production is finally given by equations, which is the summation of A1 prime into R1 prime, which is equals to summation A1 into R1. The equation suggests that the newly generated set of equations for entropy production are also same. Thus, the transformation properties of the fluxes Ji and the generalized forces Xi are such that linear combination of forces and fluxes give a new set of fluxes Ji prime and a new set of forces Xi prime. Thus, the equation holds good. Therefore, we have summation Ji Xi is equals to summation Ji prime into Xi prime. There are three types of transformations in linear irreversible thermodynamics. Now we will discuss about non-stationary states. Non-equilibrium stationary states are the state variables which are independent of time. In this case, entropy production is different from zero and there is no transport of mass, that is Jm is equals to 0. Whereas equilibrium states are the states in which entropy production is 0. A stationary state arises when the concentration of the intermediate components does not vary with time. Considering a one component system in which there exists temperature gradient as well as the concentration gradient, which are denoted by xth and xm respectively, near equilibrium, entropy production per unit time can be written as the sum of jth xth plus jm xm, which is greater than 0. And the linear phenomenological laws, which we will discuss later, are jth is equals to L1 xth plus L12 xm and jm is equals to L21 xth plus L22 xm, where L11 and L22 are the coefficient of thermal conductivity and diffusion coefficient respectively. L12 is the coefficient of heat flow related to a concentration gradient. L21 is coefficient of mass flow associated with a temperature gradient. Stationary states may be characterized by extremum principle. This principle states that in the stationary states, the minimum amount of entropy is produced compatible with some auxiliary conditions to be specified in each case. Thus, an equation may be derived that specify conditions that entropy production has minimum value for a given value of xth. Thus, using equations and Onsager reciprocal relation, which is L12 is equals to L21, the rate of entropy production becomes L11 xth square plus twice of L12 xth into xm plus L22 xm square. Taking the derivative of equation 19 with respect to xm, keeping xth constant, we get twice of L12 xth plus L22 xm, which is equals to twice of Jm. In the situation of steady state, when Jm is equals to 0, it means that the rate of entropy production has an extreme value in the steady state. This extreme is minimum, which can be shown by taking the second derivative of equation 19. As in the steady state, we know that the differential of internal entropy with respect to xm is equals to 0. We get finally twice of L22. Since L22 has a positive value, thus the second derivative is also positive, so that the extremum is a minimum. This statement also furnishes the statement of Prigoghine's principle of minimum entropy production. This principle states that at the steady state, all the flows corresponding to unrestricted forces vanish. Thus, this can be generalized to the case of n-independent affinities, out of which certain numbers are kept constant. For such stationary states, Jn is equals to 0. Such conditions are equivalent to minimum condition for entropy production, that is, differential of internal entropy with respect to xj is equals to 0. Prigogine stated that the time variation of rate of entropy production splits into two parts. First, due to the irreversible processes which are occurring inside the system, and second, due to the flow of entropy from the system to the surroundings. Because of the irreversible processes occurring in the system, the rate of entropy production decreases until the state is reached when it becomes minimum. When the system is in non-equilibrium steady state, then a system cannot come out of this state despite being spontaneous irreversible state. But if some perturbations occur that disturbs the system from steady state, then there occur some internal changes which bring back the system to the steady state. Phenomenological equation and laws. The principle of microscopic reversibility states that under equilibrium condition, any molecular process and its reverse will proceed at the same rate. According to this principle, the rates or velocities of various types of processes, that is, fluxes, are linearly related to the thermodynamic forces. Thus, these forces are responsible for the fluxes that occur. For example, the temperature gradient is responsible for heat flow. Gradient of chemical potential is responsible for diffusion of matter, and gradient of electrical potential is responsible for flow of charge. In irreversible processes, the transport of heat, mass, momentum, and electric charge occurs. In all such cases, a quantity flux is transported as a result of driving force which is divided from gradient of some physical property of the system. For transport of heat, driving flux is temperature gradient. For transport of mass, driving flux is the concentration gradient. For electric current, flux is the potential gradient. The transport phenomena of one-dimensional system is given by the relation J is equals to L into X. Linear law of this kind are referred to as phenomenological law, where J is flux, that is the flow per unit area, X is the driving force or gradient which is responsible for the flow, and L is the proportionality constant called transport coefficient. Various transport processes can be written in the relationships. For example, the Fourier's law for the heat transfer, Fick's law for mass transfer, Newton's law for momentum transfer, Ohm's law for electricity flow, and in all the equations, your Ji's represent corresponding fluxes, that is, the Jq is heat flux, Jm is mass flux, J capital M is momentum flux, and Je is the electrical flux. And kappa, d, mu and lambda are corresponding transport coefficients which depend upon the material properties of the system. The laws are called phenomenological laws, which are used to define transport processes. The forces X drive the flows a gradient of 1 by T causes the flow to heat, but at equilibrium, all the forces and flows vanish. Forces drive the flow, but a flow does not depend entirely on the forces. The flows can depend on other factors such as presence of catalyst. The catalyst can affect the rate of reaction. When two or more processes occur simultaneously in the same system, it is assumed that each of the flows depend on both the forces which cause the flow. For small deviations in the forces from their equilibrium value of 0, the flows are expected to be linear function of forces. Lord Rayleigh expressed the linear dependence of all mechanical flows on all the mechanical forces in a system. But Onsager in 1931 extended this concept and included all thermodynamic flows and forces. The resulting phenomenological equations are as follows, given by equations 6, 7 and 8. And we have Ji is equals to summation of Lik into Xk, where I is equals to 1, 2, 3 up to n. The significance of these equations can be explained. Let us consider a system in which n simultaneous flows or processes, that is J1, J2 up to Jn occurs. To each flow, corresponding conjugate forces x1, x2 up to xn were assigned. The choice of conjugate force is made in such a way that the dimension of the product Ji into Xi should be as that of dimension of entropy production or decrease in free energy with time. According to Fick, Fourier and Ohm, it is concluded that each flow is proportional to conjugate force. The proportionality constant be straight coefficient, that is Lii. All these straight coefficients appear on the diagonal of the matrix of forces on the right hand side of a set of equations given. But from equations we also state that the flow J1 is also driven by forces x2, x3 up to xn if the coupling coefficient or cross coefficient, that is L12, L13 and so on, are different from 0. That is, the force Xj contribute to flow Ji when I is not equals to j, only when Lij is not equals to 0. This shows that the dependence of flows on non-conjugate forces is also linear, and this linearity holds true only for the sufficiently slow processes occurring when the system is not too distant from a state of equilibrium. Now consider two flows J1 and J2, where J1 is the flow of heat, J2 is the flow of matter, x1 is temperature gradient and x2 is the concentration gradient. And we know that J1 is directly proportional to x1 and J2 will directly proportional to x2. If the two processes occur simultaneously and the system is close to equilibrium, the flow and fluxes are related by the phenomenological equations. That is, J1 is equals to L11 x1 plus L12 x2 and J2 is equals to L21 x1 plus L22 x2, where L11 and L22 are the direct or diagonal coefficient and are always positive, and L12 and L21 are off diagonal coefficients that describe the interference or coupling of the two irreversible processes 1 and 2. It may be positive or negative. L12 is the heat flow arising due to the concentration gradient. L21 is the flow of matter arising due to the temperature gradient. Now in general, Ji is equals to Lii xi plus Lik xk plus other terms, and Jk is equals to Lki xi plus Lkk xk and so on. According to the law of irreversible thermodynamics, the change in internal entropy with respect to time is given by summation of Jk into Xk, which is greater than 0. Considering the condition, the change in internal entropy with respect to time is equals to J1 x1 plus J2 x2. Substituting equation will give, now equation will be positive if both x1 and x2 have the same sign. Further, inequality condition which also be satisfied if L11 is greater than 0, L22 is greater than 0 and the square of the sum of L12 and L21 is less than the product of 4 times L11 into L22. The right hand side of equation may be written as equation. Now substituting L12 plus L21 divided by L11 as 2D and adding and subtracting the term d square x2 square in equation, we have equation. In this equation, the term x1 plus dx2 whole square will always be positive. Now for the term to be greater than 0, 4 into L11 L22 should be greater than the sum of L12 plus L21 whole square. Therefore, L11 is greater than 0 and L22 is greater than 0. Thus, the diagonal coefficient L11, L22 are always positive, whereas the off-diagonal coefficients may be positive or negative, their exact value being dependent on the equation. An alternative form of equation in which the forces are represented as linear function of flows can be expressed by the equations, and we have xi is equals to summation rik into jk. A set of equations are obtained by solving equation for the forces. The coefficient lik is equals to ji upon xk when all the values of xj are constant, have dimension of flows per unit force and have characteristics of mobilities or conductance. The coefficients rik is equals to xi upon jk when all the jj values are constant, have dimension of force per unit flow and represents resistance or friction. It is possible to pass from one system of coefficient to other by rules of matrix algebra. For the simple case of two flows and two forces, we have equation and the relation between the rik and lik are given by equation in which the determinant L is equals to L11 into L22 minus L12 into L21. In general, Rik is given by equation in which the numerator is the minor of the determinant corresponding to the term Lik and the denominator is the determinant of the matrix of the coefficient Lik. Now let us summarize what we have learned. The rate of entropy production is given by the sum of change in internal entropy and change in external entropy. In terms of entropy production and entropy flow, the rate of entropy production is given by the integral of sigma minus divergence of j into dV, where the integral of sigma dV represents the entropy production and integral of divergence of j into dV represents the entropy flow. The transformation properties of the fluxes Ji and the generalized forces Xi are such that the linear combination of forces and fluxes give a new set of fluxes Ji prime and new set of forces Xi prime. A stationary state is a state which arises when the concentration of the intermediate components does not vary with time, and the extremum principle states that in the stationary state the minimum amount of entropy is produced compatible with some auxiliary condition to be specified in each case. The transport process can be described by various laws such as the Fourier's laws, which state that jq is equals to minus kappa dt by dx, Fick's law, which is Jm is equals to minus d dc by dx, Newton's law, Jm is equals to minus mu du by dx, and Ohm's law, Je is equals to minus lambda de by dx, where kappa d, mu, lambda are corresponding transport coefficients which depend upon the material properties of the system, and Ji's are the corresponding fluxes. According to Fick, Fourier, Ohm, it is concluded that each flow is proportional to the conjugate force. The proportionality constant is the straight coefficient Lii. All these straight coefficients appear on the diagonal of the matrix of forces on the right hand side of the set of equations. The flow J1 is also driven by forces x2, x3 up to xn, but the flow J1 is also driven by the forces x2, x3 up to xn, that is, the force xj contribute to flow Ji only when the coupling coefficient or the cross coefficient Lij is not equals to 0. This shows that the dependence of flow on non-conjugate force is also linear. An alternative form of equation in which the forces are represented as linear function of flow can also be expressed as xi is equals to summation of Rik into Jk, where Rik is equals to xi upon Jk when all the Jj values are constant and have the dimension of force per unit flow and represent the resistance or friction. The relation between Rik and Lik is given by this expression, in which L is the determinant of the matrix of the coefficients Lik and Lik is the minor of the determinant corresponding to the term Lik.